Okay, so hi everyone and welcome back to this math reading group session. Today, thanks Evelyn again, we're covering Mamba 2 from Frida and Albert. So they've gone beyond basic Mamba, so there's some interesting exchanges and Evelyn is going to talk about it. So take it away.
Thank you. Thank you for the introduction. And again, thank you for taking a summer afternoon in North America to come listen to me talk about this. I first read this paper about 10 days ago, and I have to say it is written in a very distinctly different style than their first Mamba paper, which I believe was from December of last year. In a way that I described initially as extending a hand of friendship across the hall towards the programmers, which I think is absolutely delightful. They had a little bit of a rough reaction, particularly with reviewers, to their initial paper. And this one, I think, is just so elegant in the way that it frames what they are doing, which is very different in a way that programmers can understand. Not only is their breakthrough interesting, the math is interesting, and they're explaining it in a way that programmers can understand. And with that, I shall begin. I'm going to read the paper, though there are 4 blog posts, which are all very good as well. And I think all 4 of the blog posts could take a bit of study as well. And I will lean on this group to have a little bit more depth on, I think, their deep, I'll call it their deep insight, which is that state space models are duals of transformer models. That was the one insight besides the writing, which I found to be important and elegant. And I'll take a little look at that diagram. It's a long paper, but it's a good paper. A little diagram here. And I think I want to start with this because I think this is the core insight of the paper and the one which I found most interesting. And so, how should I put this? Currently, machine learning is using chunky boy models. We're throwing all of our data at all of our data all the time and not providing any compression. And they're wonderful because they work really well, but they take extraordinarily large amounts of resources to be able to handle these. And that's what they're considering here is the structured masked attention, which is this half of the duality chart. The state space model is applying compression to essentially what we attend to as tokens come through in time. So a state space model is not about all data attending to all data, but it's about attending to the important data as it comes in. Yes?
I just wanted to make sure that we're looking at the same thing. Right now we're at the table of contents of the blog posts.
Thank you for that. How's that one?
Much better.
So this is page 18 of the Mamba 2 paper. And thank you for interrupting. And so they're moving into a dual space with this. Instead of attending everything to everything, they're attending selectively to the tokens that are coming in as determined that they matter. I was surprised that they were able to identify a duality in this. This was the thing that surprised me most about this. And again, it opens up an entirely new computational space if we can move from something that we understand pretty well, namely transformer attention models, into something that we don't understand nearly as well yet, the structured state space models. If they are actually dual, then I think it's a remarkable and exciting premise. And with that, I'll go back to reading the paper. Does anybody have any questions about why I think this is the exciting bit?
I mean, I just agree. It is very interesting.
Okay.
Although they do mention it's
Thank you very much.
and
And now
linear attention, so it seems to be like there's a bit, maybe a tiny little bit thing missing from like proper attention.
Okay. We'll get into that later then. Even if they've done linear attention as a dual with state space models, they've still compressed the amount of computation required because state space models are using a compression to allow to attend to only some of the tokens. So it's still a big win. Back to the top. Transformers are SSMs, generalized models, and efficient algorithms through structured state space duality. This is a paper by a team which is doing absolutely outstanding these works, Trudeau and Albert Gu. Abstract. While transformers have been the main architecture behind deep learning success in language modeling, state space models, SSMs, such as Mamba, have recently been shown to match or outperform transformers at small to medium scale. We show that these families of models are actually quite closely related and develop a rich framework of theoretical connections between state space models and variants of attention, connected through various decompositions of a well-studied class of structured, semi-separable matrices. Our state space duality, SSD framework, allows us to design a new architecture, Mamba 2, whose core layer is a refinement of Mamba's selected SSM that is 2 to 8 times faster, while continuing to be competitive with transformers on language modeling. So they've made what I believe to be a pretty significant breakthrough with this paper. Introductions. Transformers, in particular decoder-only models, such as GPT and Llama, which process input sequences in a causal fashion, are one of the main drivers of modern deep learning success. Numerous approaches attempt to approximate the core attention layer to address its efficiency issues, such as scaling quadratically in sequence length during training and requiring a cache of size linear in sequence length during autoregressive generation. In parallel, a class of alternative sequence models, structured state space models, or SSMs, have emerged with linear scaling in sequence length during training and constant state size during generation. They show strong performance on long-range tasks such as S4, and recently matched or beat transformers on language models, Mamba 2023, at small to moderate scale. However, the development of state space models have appeared disjoint from the community's collective effort to improve transformers, such as understanding them theoretically as well as optimizing them on modern hardware. As a result, it's more difficult to understand and experiment with state space models compared to transformers, and it remains challenging to train SSMs as efficiently as transformers from both an algorithmic and systems perspective. Our main goal is to develop a rich body of theoretical connections between structured state space models and variants of attention. This will allow us to transfer algorithmic and systems optimizations originally developed for transformers to state space models towards the goal of building foundation models that perform better than transformers while scaling more efficiently in sequence length. A milestone contribution in this direction was the linear attention framework, Carthopoulos 2020, which derived a connection between autoregressive attention and linear RNNs by showing the equivalence between dual forms of quadratic kernelized attention and a particular linear recurrence. This duality allows new capabilities, such as the ability to have both efficient parallelizable training and efficient autoregressive inference. In the same spirit, this paper provides multiple viewpoints connecting linear complexity SSMs with quadratic complexity forms to combine the strengths of SSMs and attention. And going on to state-space duality, our framework connecting structured SSMs and variants of attention, which we call structured state-space duality, SSD, is made through the abstraction of structured matrices. Matrices with subquadratic parameters and multiplication complexity. We developed two broad frameworks for representing sequence models. One is a matrix transformation and one is a tensor contraction, which each reveal different perspectives of the duality. Our technical contributions include: we show an equivalence between state-space models and a well-studied family of structured matrices called semi-separable matrices. The connection is at the heart of our framework, revealing new properties and algorithms for state-space models. A central message of this paper is that different methods of computing state-space models can be reframed as various matrix multiplication algorithms on structured matrices. And I'm going to pop down to the illustration of what they're talking about with a structured matrix, because you will understand it when I show you. They are dealing with lower triangular matrices, and they are essentially dealing with separate blocks, equally sized blocks, but separate blocks of entries within this matrix, and a partial triangular to fill in the rest of the triangular. So they are dealing with these as blocks, and that allows for I believe they've got pretty well optimized algorithms for dealing with matrices of this form. And also with this, it may be possible to essentially not attend to this portion of the triangular matrix at all. That is, it might be possible to completely ignore a section, which would mean that you would only need to attend to far less than half of the matrix. And if that's true, it's a huge computational win. And I will go back to the top again. The second point, they significantly improve the theory of linear attention, which is Karpathodis 2020. We first provide an incisive proof of its recurrent form through the language of tensor contractions, and then generalize it to a new family of structured masked attention, which is section 4. Then they can connect state-space models and structured masked attention, showing that they have a large intersection that are duals of each other, possessing both SSM-like linear and attention-like quadratic forms. We also prove that any kernel attention method possessing a fast recurrent form must be an SSM. Does anybody have any questions or comments about what they have done in this, or what they're trying to do?
So maybe real quick. So there's this thread going through all the state space model literature, which is this idea of duality, and usually they mean that you have this architecture that has two ways to be computed. So for example, you have the RNN mode sequential evaluation, but then you can enroll that into a big matrix multiplication, and that's the same here. So it's one thread. Okay, you have and the selling point of that is that okay, you can use the chunky matrix multiplication version for training, where you can use big GPUs that can do matrix multiplications efficiently, and then for inference you can use the sequential version because it's cheaper. So is this thread going there? And I'm not entirely certain. For example, okay, they've done a lot of improving here to make it more efficient. And it's also similar to RWKV. I'm not going to try to pronounce it another way, but there's a bunch of these models claiming, okay, you can use one algorithm for training, another for inference, and at some point it's maybe difficult to understand the difference between the two. For the SSMs, of course, it's clear because there's 9, but I'm not so sure, for example, with RWKV. I don't know if you had thoughts about that. I might be
So I
completely
haven't
going at
looked at
tangent. Sorry.
I haven't looked that closely at RWKV, so I really can't comment on that. I also haven't paid much attention to the implementations of it. So I apologize, I can't comment. I do think that I agree that it is a similar pattern, that they're using one model for training and one algorithm for training and one algorithm for inference. And that is a fruitful line of investigation. Does anybody else know anything about RWKV and could comment? I will mention that the author of RWKV was involved in the MatMul-free modeling paper that came out a little while ago, and I read that, and I thought that they were onto something pretty smart with that. But again, I can't say that I'm an expert, and it may be that I am completely misreading whether or not they've had as big a breakthrough as I think they have.
So RWKV was a different direction from the paper that was matmul-free, because RWKV, its focus was on replacing the attention mechanism. And so it still takes advantage of all the developments in terms of the feed-forward layers that transformers have been using. The attention replacement they were using was specifically related to using exponential rotations to replace having to do exponential rotations of a state space. So it was kind of akin to a state space model, although I don't remember the exact math beyond that.
Yeah, I think there's like one line in the Mamba paper where they mentioned RWKV and say it's like a ratio of two SSMs. I didn't understand, like I tried to look at the RWKV equations and could not make too much sense of them, but yeah, so maybe something for another day.
Yeah, and so the short version there was they had a transformer attention style mode that could be used in training, and they had a linear state space mode that could be used at inference, and these two modes were equivalent, mathematically equivalent.
Right, so exactly the same pattern or of duality as in SSMs then.
Yeah, yeah.
And that's very interesting. I have no idea what an exponential rotation would be. I have no intuition about that at all.
So that comes from complex numbers. If you have a number e to the i x, and you increase x, then what you get is a rotation in the complex plane.
Okay,
Even
that makes sense.
for a
Thank you.
linear increase in x, you get a certain amount of rotation. And so you can apply that to vector mathematics and get rotations in vector space by doing that same thing.
So would the goal of that be to, and I'm trying to translate this back to matrix operations, would that be to concentrate the values of interest along the diagonal of the matrix? Would that be the goal of that?
No, that's not my understanding. I believe it was closer to the same idea as the rope position encoding, but you're doing it to the actual data values. And so that would let you, in a sense, select for a certain distance of data by choosing the angle at which you're evaluating the data. And maybe don't rotate on all dimensions. That way some dimensions still just carry meaning. And this I'm all fuzzy on because I never myself understood what happens when you do an exponential rotation of a I times a matrix. That's a very complex operation. E to
And
the
so
I times.
you're talking about RWKV here?
Yes.
That's what I remember from the RWKV algorithm, yes.
Interesting. I didn't realize that was like a complex space neural network architecture.
So the neural network architecture as it's exposed does not have the complex numbers anymore. It is the attention operation that takes advantage of parts of complex mathematics that results in linear operations that do more complicated operations. If that makes sense. It probably doesn't. My memory's too fuzzy on this.
I mean, this is enough breadcrumbs for me to poke around. This is really interesting. Thanks for clarifying this stuff.
Okay, I think maybe we
Yes,
should
and thanks.
stop the derailment. Sorry for starting it.
So I found this a rather nice rabbit hole. I had no idea that RWKV was using a similar pattern to this, and I found this pattern really interesting, so thank you for that. And to return to figure 1, we've got a structured state space duality, which has quite a few components, and we're probably not going to have much more time than to briefly look at all of them, which include structured matrices, which give us more efficient algorithms, attention, which is the transformer attention common pattern that we need in order to do inference. We've got state space models for training, and they're connected to structured matrices through semi-separable matrices, which we have good algorithms for manipulating. The structured masked attention, which again maps attention to structured matrices. And then the mapping between attention and state space models is the state space duality, which leads to the work here, which is Mamba 2. Any questions about that? I shall continue. If beyond its intrinsic theoretical value, our framework opens up a broad set of directions for understanding and improving sequence models. First, efficient algorithms. Our framework exposes new, efficient, and easily implementable algorithms for computing state space models in Section 6. We introduce a new state space a new SSD algorithm based on block decompositions of semi-separable matrices that take advantage of both the linear SSM recurrence and quadratic dual form, obtaining optimal trade-offs on all main efficiency axes, that is, training and inference compute, memory usage, and ability to leverage matrix multiplication units on modern hardware. A dedicated implementation of SSD is 2 to 8 times faster than the optimized selective scan implementation of Mamba, while simultaneously allowing for much larger recurrent state sizes, 8x the size of Mamba or even higher with minimal slowdown. SSD is highly competitive with optimized implementations of softmax attention, that is flash attention, which was Dow 2024, flash attention 2, crossing over at sequence length 2000 and 6x, 6 times faster at sequence length 16,000. So I have to say that this is a pretty impressive improvement in less than 6 months from this team. Architecture design. One major obstacle to adopting new architectures such as state space models is the ecosystem tailored to transformers, such as hardware-efficient optimization and parallelism techniques for large-scale training. Our framework allows using established conventions and techniques for attention to build a vocabulary of our architecture design choices for SSMs and further improve them. For example, we introduce the analog of heads from multi-head attention to SSMs. We show that the Mamba architecture is a multi-input SSM, MIS, that turns out to be analogous to multi-value attention, and compare other variants of Mamba with different head structures. We also use these ideas to make slight modifications to the Mamba block, which allows tensor parallelism to be implemented in the style of Megatron. The main ideas include grouped value attention, GVA head structure, and moving all data-dependent projections to occur in parallel at the beginning of the block. The combination of the modified parallel Mamba block together with using SSD as the inner SSM layer results in the Mamba 2 architecture. We investigate Chinchilla's scaling laws for Mamba 2 in the same setting as Mamba, finding that a Pareto dominates Mamba and Transformer++ in both perplexity and wall clock time. We additionally train a family of Mamba 2 models at various sizes on the pile, showing that it matches or outperforms Mamba and open source transformers on standard downstream evaluations. For example, Mamba 2 with 2.7 billion parameters trained on 300 billion tokens on the pile outperforms Mamba 2.8 billion, Pythia 2.8 billion, and even Pythia 6.9 billion trained on the same dataset. And both Pythias are transformer attention models. Mamba 2.8 is a Mamba model, state space model. Systems optimizations. The SSD framework connects state space models and transformers, allowing us to leverage a rich body of work on systems optimizations developed for transformers. For example, tensor parallelism is an important model parallelism technique to train large transformer models by splitting each layer across GPUs on the same node. We designed Mamba 2 to be TP friendly, reducing the number of synchronization points per block by half, and that will be a huge speed up. For very long sequences whose activations do not fit on one device, sequence parallelism has been developed for attention blocks. We describe how to train SSMs in general and Mamba 2 in particular with sequence parallelism by passing the recurrent states between devices. And that's going to be a fairly small amount of data passing between, and it will be slow because anytime you pass between devices, it's slow, but it'll be much faster than moving the entire data state for several billion parameters across devices. For fine-tuning with examples of different lengths, for best efficiency, Transformer requires sophisticated techniques to remove padding tokens and perform attention on variable length sequences. We show how Mamba 2 can be trained with variable sequence lengths efficiently, requiring no padding tokens. And anytime you get rid of a padding token, it's a win because you don't learn anything from a padding token, but it costs you data movement and compute. Section 9 empirically validates Mamba 2 on language modeling, training efficiency, and a difficult multi-query associative recall task. Finally, in Section 10, we provided an extended related work and discussed potential research directions opened up by our framework, and they have open sourced their model code and pre-trained checkpoints. Is everybody familiar with state space models here, or do I need to go through this again?
I mean, given that we've had several sessions on state space models, I would hope that people have the basics, at least.
Okay, then I will skip down to continuous time models and skip that paragraph. The original structured SSMs originated as continuous time maps on functions x of t, which is drawn from the real numbers, outputting to y of t, also in the reals, rather than operating directly on sequences. That is, state space models were operations on functions, not sequences. In the continuous time perspective, in equation 1a, the matrices A and B, and in this paper, they are not using the bar notation from the original Mamba model. Consider A and B to be A bar and B bar. The matrices A and B are not directly learned but generated from the underlying parameters A star and B star, along with the parameterized step size delta. The continuous parameters, that is delta, A star, and B star, are converted to discrete parameters, A and B, through a fixed formulas. A equals a formula on A for delta and A star, and B equals a formula on B of delta and B star, where the pair FFA and FFD is called a discretization rule. And they're talking about the A bar and B bar. Recurrent models. Equations 1 and 2 take the form of a recurrence, which is linear in its input x. Structured state space models can therefore be viewed as types of recurrent neural networks, where the linearity endows them with additional properties and allows them to avoid the sequential computation of traditional RNNs. And that I don't understand. Does anybody have a comment on that? I don't know why a state space model would allow them to avoid the sequential computation of RNNs. Is it because of the hidden state that the state space model has?
So maybe if you
I
go
assume
back,
it has. Oh, sorry.
sorry. So if you go quick back to the like equations 1 and 2, as I mentioned. So this is the basic like generic equation of a structured state space models, and it's basically all linear operations. So like the equations here, you could interpret them as a sequential transform, so basically an RNN, but a linear RNN, meaning there's no like activation. There's no non-linearity between like the states and variables at times t and t plus 1. And that allows you exactly this idea of duality, where you can unroll all the operations into one very big matrix. So here your input is the sequence xt, and you only care about yt. And so we can represent the map from xt to yt as just it's a linear map, so it's just one big matrix. And so that's what they mean, that when you can unroll this into a single operation and you avoid you avoid, at least for training, having to do this sequential algorithm. Hello?
Yes, I'm still pondering that. I understand that state space models are linear in that they are simply doing linear operations and nothing which resembles products of values in different parts of the sequence. But I think the part I don't understand is the part about the sequential computation of traditional RNNs. And it may be that I haven't studied RNNs well enough.
So if you look at these equations, right, they tell you, okay, you have an input sequence xt, and you care about the output sequence yt, which you compute from xt. And you do that by having a hidden state ht. And the way it works is, okay, you start from x0, and you say, okay, let's say h0 is 0 or whatever, and then you update the hidden state at time t plus 1 based on based on time t. And the basic algorithm would be like doing this equation like step by step. So from t1 you do you do computation, for t2 and so on. So that would be a sequential algorithm for computing the SSM, and it's equivalent to an RNN, at least a linear RNN with no nonlinearity.
Okay, that makes sense. Thank you.
But because it's linear, you can just also like make a very big matrix out of your steps, and it's equivalent.
A very big vector. A is a square matrix. H is a vector.
Yeah, but it's more like if you look at the in the blog post, they show like this triangular matrix with the products of the ATs, right? That's the same idea.
Yes.
They're unrolling all the sequential steps into a very big transform.
Okay.
And that you can do that because it's linear, so there's no non-linearity in between.
I understand. Thank you. Does anybody else have any questions about this? I know I hijacked us a little bit. I shall continue. Conversely, despite this simplification, state space models are still fully expressive as sequence transformation in the sense of universal approximation. Convolutional models. When the state SSM's dynamics are constant through time, the model is called linear time invariant. In this case, there are equivalent to convolutions. The state space models can be viewed as types of CNNs, but where the convolution kernels are implicitly parameterized through the state space model parameters A, B, and C. And second, the convolution kernels are generally global instead of local. Conversely, through classical signal processing theory, all sufficiently well-behaved convolutions can be represented as SSMs. That I found interesting. Commonly, previous linear time invariant state space models would use the convolutional mode for efficient parallelizable training, where the whole input sequence is seen ahead of time, and switched into recurrent mode for efficient autoregressive inference, where the inputs are seen one step at a time. And now we go to selective state space models. The form of equation 2, where the parameters A, B, and C can also vary in time, was introduced in Mamba as selective SSM. Compared to the standard LEI formulation, this model can selectively choose to focus on or ignore inputs at every time step. It was shown to perform much better than LTI SSMs on information-dense data, such as language, especially as the state size n increases, allowing for more information capacity. However, it can only be computed in recurrent instead of convolutional mode and requires a careful hardware-aware implementation to be efficient. Even so, it is still less efficient than hardware-friendly models such as CNNs and transformers because it does not leverage matrix multiplication units, which modern accelerators such as GPUs and TPUs are specialized for. And so that points out a big opportunity, which is that Mamba models are going to need new hardware. While time-invariant SSMs are closely related to continuous, recurrent, and convolutional sequence models, they are not directly related to attention. In this paper, we show a deeper relationship between selective state space models and attention and use it to significantly improve the training speed of SSMs while simultaneously allowing for much larger state sizes n. Structured SSMs as sequence transformations. First definition, we use the term sequence transformation to refer to a parameterized map on sequences y of f of theta of x, where x and y are both in R to the t comma p, and theta is an arbitrary collection of parameters. T represents the sequence or time axis, subscripts index into the first dimension, that is x sub t and y sub t are in R to the p. Sequence transformations, that is SSMs or self-attention, are the cornerstone of deep sequence models where they are incorporated into neural network architectures, that is transformers. The SSM in 1 or 2 is a sequence transformation with p equals 1. It can be generalized to p greater than 1 by simply broadcasting across this dimension. In other words, viewing the input as p independent sequences and applying the SSM to each. One can think of p as a head dimension, which they'll elaborate later. In definition 2.2, we define the SSM operator SSM on A, B, and C equals the SSM at the sequence between A0 and the terminal time, B0 and the terminal time, and C0 at the terminal time as the sequence transformation of X in RTP mapping to Y in RTP as defined in equation 2. In SSMs, the n dimension is a free parameter called the state size or state dimension. We also call it the state expansion factor because it expands the size of the input and output by a factor of n, with implications for the computational efficiency of these models. Finally, we remark that many types of sequence transformations, such as attention, can be represented as a single matrix multiplication across the sequence dimension. Any question about the first two definitions? Sequence transformation and the SSM operator? Okay. Definition 2.3, we call the sequence transformation y for f of theta on x a matrix transformation if it can be written in the form y equals m of theta times x, where m is a matrix dependent on the parameters theta. We identify the sequence transformation with the matrix M and often drop the dependence on theta when it's clear from context. That's a little bit more of a housekeeping definition. Attention. Attention broadly refers to a type of computation that assigns scores to every pair of positions in a sequence, allowing each element to attend to the rest. By far the most common and important variant of attention is softmax self-attention, which can be defined as y equals the softmax of the query matrix times the key matrix transposed, and all of that times the value matrix for the query key and value in R, T, and P. So they're all the same size as what they defined above. The mechanism of pairwise computations induced by materializing the query key transpose leads to the characteristic quadratic training cost of attention. Many variants of attention have been proposed, but all share the underlying cost of these attention scores with various approximations. The most important variant for this work is linear attention. Roughly speaking, this family of methods drops the softmax by folding it into a kernel feature map and uses associativity matrix multiplication to write the query key transpose times value to query times the key transpose times the value. Moreover, in the important case of causal autoregressive attention, they show that when the causal mask is incorporated to the left-hand side as L composed with the query key transpose times value, where L is the lower triangular ones matrix, then the right-hand side can be expanded as a recurrence. And so this is a filter that they're applying here. Several recent and concurrent works, such as RetNet and Gape Loop, strengthen this to more general forms of L. In this work, our formulation of structured masked attention will strongly generalize this idea. And so any questions about what they're doing with linear attention here?
Just a quick notation question. So when they write L circle, or so in the definition, so yeah, L circle Q K T. So what does the circle mean here? So I think it means apply the attention mask to each head. So it's not exactly a matrix multiplication, but like almost.
So I'm going to guess here, and I apologize if I'm wrong, but I think they're meaning a tensor contraction.
Oh, I thought it was like a Hadamard product.
Yeah, that's basically what I think is happening, right?
Right,
Oh,
it's this
okay, multiplied
binarization.
Element-wise.
Okay, so it's not even Hadamard, it's just...
So
Actually, is Hadamard element-wise?
Yeah, I think that's what I meant by Hadamard anyway. I think is element-wise.
Right,
I
okay,
think it's just
I might be
element-wise.
confusing with another
that was my
Hadamard.
error.
Anyway, okay, thanks.
Sorry. What's Hadamard?
That was my error. So I called this a filter because of that. It's element-wise.
Okay, thanks for clearing that up.
You're welcome. And thanks for calling me out. I was unclear. Structured matrices. General matrices M and R, T and T require t-squared parameters to represent and big O t-squared time to perform basic operations such as matrix vector multiplications. Structured matrices are those that can be represented in subquadratic, ideally linear parameters through a compressed representation. And second, have fast algorithms, most importantly matrix multiplication, by operating directly on this compressed representation. Perhaps the most canonical families of structured matrices are sparse and low-rank matrices. However, there exist many other families such as Toplish, Cauchy, Vandermonde, and butterfly matrices, which have all been used in machine learning for efficient models. And I haven't read any of these papers. Structured matrices are a powerful abstraction for efficient representation and algorithms. In this work, we will show that state space models are equivalent to another class of structured matrices that have not previously been used in deep learning and use this connection to derive efficient methods and algorithms. And so the structured state space duality. This paper develops a much richer framework of connections between state space models, attentions, and structured matrices. We provide a brief summary of the main method, which is actually quite self-contained and simple algorithmically. The recurrent linear form. The state space dual SSD layer can be defined as a special case of the selective state space model. The standard computation of an SSM as a recurrence or parallel scan can be applied, which has linear complexity and sequence length. Compared to the version used in Mamba, SSD has two minor differences. The structure on A is further simplified from diagonal to scalar times identity structure. Each A sub t can also be identified with just a scalar in this case. And second, we use a larger head dimension p compared to p equals 1 used in Mamba. Typically, p is either 64 or 128 is chosen, which is similar to conventions for modern transformers. They don't talk anything more than this about how they pick that or how large it can be. Compared to the original selective SSM, these changes can be viewed as slightly decreasing the expressive power in return for significant training efficiency improvements. In particular, our new algorithms will allow the use of matrix multiplication units on modern accelerators. That's pretty huge. Any questions about this? This, I think, is a massive improvement. It goes from a big square matrix to a scalar. Dual quadratic form. The dual form of SSD is a quadratic computation closely related to attention. So we've got L element-wise multiplied with a query times key transpose, all multiplied by V, where L is a product over A, where I is greater than J, and otherwise 0. That is, this is a lower triangular matrix. And A sub I are input-dependent scalars bound between 0 and 1. Compared to standard softmax attention, there are two main differences. The softmax is dropped, and that is absolutely huge. The attention matrix is multiplied element-wise with an additional mask matrix L. Dropping the softmax is probably the most computational improvement here, because it's an expensive operation which requires looking at the entire row in order to calculate the value, which means it requires a GPU requires a synchronization step to ensure that you're attending to all of the current values of the row, which may be very large and may require quite a bit of data movement to be able to do. So getting rid of this is huge. And applying the mask matrix to the attention matrix is simple to do in modern hardware. Both of these changes can be viewed as addressing problems within vanilla attention. For example, the softmax has been recently observed to cause problems in attention scores, such as the attention sink phenomena in Darcet 2024 and Zhao 2024. More importantly, the mask matrix L can be viewed as replacing the heuristic positional embeddings of transformers with a different data-dependent positional mask that controls how much information is transferred across time. More broadly, this form is an instance of our structured masked attention generalization of linear attention as defined in section 4. Any question about the dual form of this?
I'm mostly just wondering about, okay, they dropped the softmax and it's cheaper, but it seemed to me that the softmax was an important bit in attention. So, okay, it's cheaper, but it's not clear to me what you lose here.
So they're replacing it with the filter matrix mask. And the operation that the mask uses is simply how shall I describe this? It's a local operation, not a global one, which softmax is. The signal contained within the matrix along the diagonal to the masking. They're entirely discarding the upper portion of the matrix because they don't need it. I don't know if that little segue helped at all.
I mean, the upper part is just the causal part, but as far as I understand, okay, that lower part matrix is also there in linear attention. It's just that now they're modulating the weight. So I think you can argue that this modulating the attention mask might be a good replacement for the softmax, but that's one thing that's not entirely clear yet for me.
Okay. I shall keep going then. Perhaps they will explain it better than I can. A little bit further up here. Here we go. So matrix form and SSD algorithm. The various forms of SSD are connected through a unified matrix representation by showing that SSMs have a matrix transformation form y equals mx for a matrix m sub theta, parameterized by theta in the real numbers t by t, that depends on theta equal a, b, and c. In particular, the dual form of SSD is equivalent to naive quadratic time multiplication by the matrix M, and the recurrent form is a particular efficient linear time algorithm that leverages the structure in M. Going beyond these, any algorithm for multiplication by M can be applied. Our proposed hardware-efficient SSD algorithm is a new structured matrix multiplication method that involves block decompositions of M, which obtains better efficiency trade-offs than either pure linear or quadratic forms. It's relatively simple and easy to implement compared to general selective SSMs, and listing one provides a complete implementation in a few lines of code. I'm going to go to that because it's really elegant, not that long. If it's at the end here. I've lost it. I'll go back here. Sorry about this. I'd explain things a little better about the structured mask.
Yeah, I like
So
that.
okay, let's spend some time on this then. The mask is going to vary according to what they are trying to get out on the other side. Linear attention uses a causal mask where every value in the lower triangle is essentially passed through unchanged. A decay mask attends closer to the diagonal than to the corner, and so weights more highly values closer to the diagonal than in the corner, and that's a retentive network. Their proposed is a one semi-separable where the values closer to the diagonal are more highly weighted and the values farther away are less highly weighted but in a block form. And that is the weighting that you get from that. Toplets is a series of diagonals which have fairly widely varying values. That is, they are not smoothly varying. And that gets us toplet structured attention. The discrete Fourier transform, which I called the summer and winter weaving pattern, gives a Fourier structured attention, which I haven't seen anything about yet. And so this is actually it fits within the different patterns that have already been looked at for different attention models. But I think this is kind of elegant and definitely a novel contribution. Does anybody have any questions about this?
My one comment about this and why I like it so much is how it really illustrates how by doing their simple like pairwise product thing that it turns one of the matrices into a mask and it's directly interpretable as a mask. That's all.
I think it's wonderful that the signal processing people have joined the machine learning community. This is signal processing.
Could I ask a quick question? Why is it beneficial to more highly weight, I guess, the weights along the diagonal?
So you can think proximity to the diagonal as proximity in time. So like if things are like closer in the sequence, closer together in the sequence, they'll be closer to the diagonal, and then as you shrink that distance, it becomes identity, and you have the identity across the diagonal.
Oh, okay, gotcha. So if you are prioritizing weights along the diagonal, you're essentially shrinking sort of like the scope of the attention almost.
Yeah, so you can like if you look up at the second row where it's decay mask, you can like kind of think of that essentially as like a Gaussian kernel. So if you extended the darker part of the mask, that would be like having a like Gaussian kernel over like the recent history that like increases the sliding window.
Okay, okay, gotcha. That makes a lot of sense. Thank you.
Yeah, the mask is like literally just a window in time.
Okay, so I see. This is where sort of like the time kind of
Yeah.
speak is
So if
coming
you
from.
if you have if you have structure in the way that you are reviewing the sequence, like if you're convolving a kernel over it, it's really easy to represent that using matrix structure, and that's what they're exploiting here.
I see. Thank you.
And the additional little bit of structure they add here, rather than a smooth decay, allows for much faster calculation of this. I'm still going to look for listing 1 though, because it was nice. And this is their algorithm. I'll come back to that. Okay, listing 1. And they give a full PyTorch implementation of their code, which was very similar to the original Mamba model. Let's see. The segsum is applying a lower triangular mask of 1s of size t and t, where t is the size of the input. They're doing a cumulative sum over the x, and the segmented sum is the cumulative sum minus so this is a difference between 2 cumulative sums on the x. One which is between the current location and one which is to the current location. So they're masking I believe this to be referring to the lower triangular portion of the x. That's what that will be. And then the mask, which we've looked at, and then they're doing a masked fill of the mask and torch infinities, and that's the segsum. The SSD has the inputs, the A, B, and C matrices, the block length of 64, which could also be 128, depending on how they want to parameterize this. The initial states are none. X is of a batch, has 4 parameters: batch length, number of heads, and D head. A, it has a batch, a length, and number of heads. B has a batch, a length, number of heads, and D state, as does C. And the return is the batch, the length, the number of heads, and the D head. They're all of the same type. And the shape is modulus of the block length. And there's no missing values. It evenly fits into that. We arrange it into blocks. I like that they're using einsum notation for this. Again, that's part of what I thought they were attempting to communicate more clearly to programmers. They're rearranging the columns of A. They're doing a cumsum again over A. They compute the output for each inter-chunk, the diagonal blocks. And then they're doing multiple chained einsums to reorder everything to give C, B, L, and X. And that produces the Y on the diagonal. Then they compute the state for each inter-chunk. So they're doing it chunk at a time, which is the right term of the low-rank factorization of the off-diagonal blocks, and that is 8 terms, the B terms. The decay state is the torch exponential of the A cumsum over the initial 3 dimensions and the last dimension but 1, minus the original cumsum for A. And the states is the torch einsum, again, multiple through to it a reordering here of B, the decay states, and X. Then they compute the inter-chunk SSM recurrence, which provides the correct SSM states at the chunk boundaries, which is the middle term of the factorization of the off-diagonal blocks, or A terms. If it's none, you just pass it through. If there are states, you concatenate the initial states and the states. Decay chunk is the torch exponential of the segsum of f dot padding of the A cumsum for all dimensions through to the 1 of 1 or 0. The new states equals the torch einsum of the decay chunk and the states, again doing a multiplication and a reorder. States are, and final state are the new states in 2 dimensions, all but 1, and the new states in 1 dimension, all but 1. And then we compute the state and the output conversion per chunk, which is the left term of the low-rank factorization of the off-diagonal blocks, or the C terms. We've got a state decay out, which is the torch exponential of the A cum sum. And then the y off, which equals torch I'm sum, again, multiplication and then reordering of C states and state decay out. And then they add the output of the intra-chunk and inter-chunk terms, off-diagonal blocks, which is a rearrange of the y diagonal plus the y off, and an ein sum leading to a reorder and return the y. Any questions about what they're doing here with their code? I really appreciated that they used modern PyTorch form for this. One of the things that they did in the original Mamba paper was provide 3 separate implementations of Mamba, including a CUDA optimized one. And I thought it was really a kindness to the community to provide a PyTorch example, which was what I thought was really obvious to someone who's done this before. Any questions about this?
So I don't really have a question, but just checking with time here. So you mentioned you have something soon. So
No, I have an hour 15. I'm good on time.
okay, perfect.
Does anybody have any questions about this? I shall return to where we were. Talked about that. About that. I think we were here. And we've talked about this, so notation. I think I will skip the notation. They're using Python-style indexing, which nobody will be confused about. And they're using typewriter fonts to denote dimensions and tensor shapes. Tensor contractions. We will heavily rely on tensor contraction or ein sum notation, both for clarity and as a central tool in stating and proving our results. We assume the reader to be familiar with this notation, which is commonly used in modern tensor libraries such as NumPy. For example, we can contract mn and nk to mk to denote the matrix multiplication operator, and in our notation contract mn nk to mk for x and y, which is equivalent to x times y. And it's in code numpy.einsum. We've got a tick mn nk to mk for x and y. And there's another glossary in Appendix A. State space models are structured matrices. This section explores different perspectives of the state space model as sequence transformation and outlines properties and algorithms of such maps. The main results of this section are about the equivalence between state space models and a family of structured matrices called semi-separable matrices, which imply new efficiency results. And that's theorems 3.5 and 3.7. The matrix transformation form of state space models. Recall that our definition of a state space model is defined as a parameterized map through equation 2. Our theoretical framework starts by simply writing this transformation as a matrix multiplication mapping the vector x in R to the t to y in R to the t. By definition, the hidden state at 0 is the B matrix 0, x 0. By induction, the hidden state at the next time equals A sub t through A sub 1 times B sub 0, x sub 0. That is the first A times the initial hidden state plus A at the next time step, and then continuing A2 multiplied by B1, x1, continuing to sum And we've got AT times AT minus 1, BT minus 2, XT minus 2. So they've doubled the A term here. And then finally, we've got A sub t at B times B t minus 1 times xt minus 1 plus, and they lose the A term at the end, bt and xt, which is the sum from s equals 0 through to t of A from t through s times b at s and x at s. So the hidden state is a recurrence relation on the input and the A matrix. Multiplying by C sub t to produce Y sub t, that is, we need to multiply by C to get the output, and vectorizing the equation over T in the dimension T, we define the matrix transformation form of SSMs. The output Y sub t equals the sum over S equals 0 to T of C sub t, and this is not, I believe this is not a transpose here, is it? Times A sub t for s of x times b sub s and x of s. So Y is the state space model over A, B, and C parameterized by x, which equals m of x, m times x. And m sub ij is defined to be equal as c sub j, I think this might be transposed, times a sub j through a I plus 1 times b sub I. So note that this is a multiplication, not an add here. And we're only attending to the lower triangular. Continuing. Semi-separable matrices. M in equation 3 is a particular representation of a class of matrices known as semi-separable matrices. Semi-separable matrices are a fundamental matrix structure. We first define these matrices and their properties. 3.1. A lower triangular matrix M is n semi-separable if every submatrix contained in the lower triangular portion that is on or below the diagonal has a rank at most n. We call n the order or rank of the semi-separable matrix. Definition 3.1 and other forms of related separable structure, that is quasi-separable matrices and other definitions of semi-separable matrices, are sometimes called structured rank matrices or rank structured matrices because they're characterized by rank conditions on their submatrices. Semi-separable matrices have many structured representations, including the hierarchical semi-separable HSS, sequential semi-separable SSS, and Bruhat forms. We will primarily use the SSS form.
So that was a lot of information. Is everyone kind of like absorbed like all of that, or should we talk about what some of that meant? We good? Okay.
I mean,
Making sure.
the first bit is just basic SSM stuff.
Yeah. All right. Sorry for interrupting.
No problem.
Oh, no, you're good. I hadn't heard of these varieties of matrices, but they aren't actually important to the rest of the paper. They're just showing off a little. It's good, though. The important part is that this lower block is evenly divisible into the size of the larger matrix, I think is the big point. Maps into this. I think, well, this is 52 pages. I think they're just dotting every single I and crossing every single T with this paper. And 4 blog posts. And well done. Well done. 3.2.1, the sequentially semi-separable SSS representation. 3.2. A lower triangular matrix M in R T to the T, T to T, has n sequentially semi-separable representation, SSS, if it can be written in the form MJI equals C sub j transpose times A sub j all the way through to I plus 1 times B sub I. Vectors B0 through B t minus 1, C0 through T C t minus 1, which are both in R to the n, and matrices A through A t minus 1 is in R n to the n. That is, these are vectors and this is a square matrix. We define the operator SSS so that M equals SSS for A over 0 through T, B 0 through T, and C 0 through T. That is everything we've seen so far. And that means that we can deal with this no matter how large it gets, because we're always attending to a lower triangular matrix that has a specific property of decomposition. A fundamental result of semi-separable matrices is that they are exactly equivalent to matrices with SSS representations. One direction can be deduced with a simple constructive proof. And then it's lemma 3.3. An n SSS matrix M with representation from equation 4 is n semi-separable. And the proof, if you consider any off-diagonal block, M in J through J prime, I prime through I, where J prime is greater than J, which is greater than equal to J, which is greater than greater than equal to I, which is greater than equal to I prime. This has an explicit rank n factorization, and they will go through the math here. But again, I believe that this illustrates it. And this works because they're only considering the lower triangular. And the rank n factorization is going to fit within the lower triangular here. Equation 5 will be used extensively in deriving our fast algorithms for sequent models. The other direction is well established in the literature on semi-separable matrices. Proposition 3.4, every n semi-separable matrix has an n SSS representation. Note that although definition 3.2 involves big O n squared times t parameters for the representation, in particular to store the A matrices, it can actually be compressed down to big O of nt parameters, which is asymptotically tight. Therefore, in the rest of the paper, we will conflate the structured matrix class, definition 3.1, and a particular representation of it, definition 3.2. So they're not going to be very formal here. We will always use this representation instead of other candidates. In turn, we'll refer to NSS to refer to an n semi-separable matrix in SSS form. Semi-separable matrices are a fundamental matrix structure and have many important properties. They are deeply related to occurrences at large and can be defined by multiple characterizations, that is definitions 3.1 and 3.2, which reveal different connections and efficient algorithms for them. We mentioned some of their other properties in Appendix C1. The notion of semi-separability is very broad, and many similar but subtly different definitions appear in the literature. Our definition may differ slightly from other conventions. First, because we are primarily concerned with causal or autoregressive settings in this paper, we have restricted the definition of semi-separability to the triangular case. Definition 3.1 more formally might be called n,0 semi-separability by some authors. Some authors may also instead refer to it as a form of quasi-separability, and they point to survey papers. One semi-separable matrices, the scalar SSM recurrence. we will single out the special case of 1SS matrices. Note that in this case, the C sub j and B sub I are scalars, and this can be factored out of the SSS representation. That's equation 4. We also use lowercase to emphasize that the parameters are scalar in this case. So we got a state space model on scalars A, B, and C, which equals the diagonal of C times M times the diagonal of B, where Mij equals A, Ij for X. So one of the things I found amazing about this paper is they've compressed from vectors down to scalars for doing the majority of the operations. Since diagonal matrices are easy to handle, that is, multiplication by a diagonal matrix is the same as element-wise scalar multiplication, we can ignore these terms. Thus, our basic representation of a 1SSS matrix is Mij equals A j through I, or a lower triangular matrix with 1 on the diagonals, and the lower diagonals being the entries for A correspond to the position in the matrix, where each row adds a different product term on the scalars. Again, this is all scalar products here. The second row has A2 times A1 through A2. The final row has A t minus 1 through multiplied through A1 and all the way through to A t minus 1. And so all they're doing here is an element-wise product. There are no big matrix multiplications in this algorithm at all. The importance of 1SS matrices lies in their equivalence to the minimal form of scalar recurrence. The case of a degenerate SSM with state dimension n equals 1 and no BC projections. They are the minimal form of a scalar recurrence. Note that multiplication y equals mx can be computed by the recurrence, and then equation 7 gives y equals a t through 0 times x 0 plus all the way through to a t through t times x of t. So you're doing a product of scalars and a sum. And reordering the terms, we get a sub t times y t minus 1 plus x sub t for 7. And that gives us this figure 2, which we've looked at before, but I'll now talk about the caption. As sequence transformations, state space models can be represented as a matrix transformation M in RTT, acting on a sequence dimension T, sharing the same matrix for each channel in a head. And so the head dimension is T here, and this input matrix X is the same, and the output matrix Y's, again, there are multiple of these corresponding to the head dimension. The inputs are transformed to the outputs through a matrix multiplication, which is actually a multiplication of scalars in a lower triangular matrix. And I found this surprising. They act on the same sequence dimension T, yes? Think of this as, like a movie. You're being presented with an image. The image is changing through time. You're looking at the whole scene at once. And so this is really a global CNN, not a partitioned one. This matrix is a semi-separable matrix, right, which is a rank structured matrix where every submatrix contained on and below the diagonal the blue, has a rank at most n, which is equals to the n and m state dimensions. And again, in their example, they use 64, 128, and they could go larger. Again, now that we've visited this for the third time, does anybody have any questions about this?
So maybe something
The head
about
dimension P is going...
Sorry.
Yes?
So something about this whole partitioning. So I'm assuming that this whole semi-separable thing, I haven't really looked into it too much. The point of this is that you can leverage matrix multiplications without necessarily having to materialize the whole big matrix. That's what my impression of what's going on here, that you can factor it and use just the small blocks. And so you can use matrix multiplications without
Yes.
having a very, very big matrix.
Correct, because all of these operations are element-wise.
Right, okay.
Does anybody else have any questions about this? This is the one of the core contributions of the paper. Note there's nothing resembling a row-wise operation here. The largest span of any operation is the n, 8th dimension. These are all element-wise operations, and there's nothing requiring a matrix by matrix multiplication. These are all element-wise scalars. And that's part of the reason why they can get such a dramatic speed up, and I think they climbed 2 to 6 times. And that they are using a block decomposition here means that each of these blocks can be assigned to different GPUs. Because there's very little, and then the results come back with very little, there is no dependence between these blocks in the calculation. Yeah, it's a completely new way of looking at both state space models and transformer models. This is not a transformer attention model. This is an elegant and fast thing. I shall continue. We thus also refer to matrix multiplication by one SS matrices as the scalar SSM recurrence or the cum-prod sum, cumulative product sum, a generalization of cumulative product and cumulative sum operator. As the fundamental form of recurrence, multiplication by one SSS matrices is important as a building block for our main algorithm. We emphasize that one of the central themes of this paper is that many algorithms on sequence models can be reduced to structured matrix multiplication operators, algorithms. The 1SS matrices exemplify this connection. There are many fast algorithms for computing the primitive scalar recurrence or cum-prod sum operator, and all of them turn out to be equivalent to different structured factorization of 1SS matrices. And there's more details in Appendix D-B. Again, this is kind of the first core idea you need to get out of this paper. All of these blocks can be separately calculated on GPUs because they do not depend on any other values than the values within their region. And they can be computed extremely quickly because they are all element-wise, which means every value only depends on itself. This is completely not what transformer attention looks like, where every value depends on every other value through the softmax. 3.3. State space models are semi-separable matrices. Recall that our definition of a state space model is defined as a parameterized map through definition 2.1. The connection between state space models and semi-separable matrices follows from simply writing this transformation as a matrix multiplication, mapping the vectors x to y in Rt. Equation 3 directly establishes the link between state space models and the sequentially semi-separable representation, which in turn are equivalent to semi-separable matrices in general. Theorem 3.5, the state space model transformation Y is a state space model on A, B, and C parameterized by X with state size n is identical to matrix multiplication by an n-SS matrix in a sequentially semi-separable representation Y equals SSS for A, B, and C times X. In other words, the sequence transformation operation, SSM, which is definition 2.2, coincides with the matrix construction operator SSS, definition 3.2, and we could use them interchangeably, or sometimes SS as shorthand. Furthermore, by a twist of fate, structured state space models and sequentially semi-separable matrices have the same acronyms, underscoring their equivalence. Conveniently, we can use any of these acronyms, state space model, SSM, or semi-separable matrix, SSS, structured state space, or sequentially semi-separable, SS, or state space, or semi-separable, interchangeably to unambiguously refer to either concept. However, we'll generally use the convention that SSM refers to state space model, SS refers to semi-separable, and SSS refers to sequentially semi-separable. And this is a bit of a kindness, but also a kind of a bit of a joke. Anyway. And figure 2 illustrates the sequence transformation perspective of state space models as semi-separable matrices. Any questions about their notation here or their joke? I shall continue. 3.4, computing state space models through structured matrix algorithms. The reason theorem 3.5 is important is that it will allow us to reduce the problem of efficient computation of state space models and other sequence models into efficient algorithms for structured matrix multiplication. We briefly provide an overview and defer our main new algorithm to section 6 after showing the equivalence of state space models to other sequence models in sections 4 and 5. As previously defined, semi-separable matrices, that is rank structured matrices, are a classical type of structure matrix. First, they have compressed representations such as the SSS form, which only has big O of t instead of big O of t squared parameters. Second, they have fast algorithms operating directly on the compressed representation. Furthermore, the parameterization and matrix multiplication cost can be tight in a semi-separable order. Proposition 3.6, an n-SS matrix of size t can be represented as big O nt parameters and has matrix vector multiplication in time and space, that is big O nt. For example, 1-SS matrices illustrate the essence of this connection. Matrix M in 1-SS for A is defined by exactly t minus 1 parameters, that is A0 through t minus 1 equals A sub 1 through A sub t minus 1, and can be computed in big O t time following the scalar recurrence. So this is very fast. The linear recurrent mode, proposition 3.6, can easily be seen in the case of diagonal structured SSMs for SD, GU, and GUPTA 2022, simply by leveraging the state space model formulation 2 and unrolling the recurrence. We provide the formal tensor contraction algorithm in 8, where the dimension S is equal to T. Okay, so we've got Z, which is a contraction of SP and SN, which gives SPN over X and B, and that's S and P and N. We've got big H, which is a contraction of TSN and SPN giving TPN over L, which is the ones, and the Z, which we calculated just prior. And Y, which is the output, equals the contraction of Tn and TPN giving Tp over C and the hidden state H in the size of T and P. That's HC. Here, L in RTT is defined as 1 SSA over A, or L sub 0 through T and 0 sub T, which is 1 SS for A, 0 through T for I in N. This algorithm involves 3 steps. Corresponding to equation 2, expanding the input X by the input matrix B, which is 8A, unrolling independent scalar SSM recurrences, which is 8B, and contracting the hidden state H by the output matrix, which is 8C. Note we've used the equivalence between scalar SSMs and 1 SSM SS matrices in 8B. We note that 8 is a special case of the Mamba S6 model. However, naive implementation is slow because of the expanded tensors Z and H of size TPN. Guindao 2023 introduced a hardware-aware implementation to avoid materializing these tensors. Surprisingly, Theorem 3.5 and Proposition 3.6 immediately imply that all state space models have the same asymptotic efficiency as algorithm 8. And anybody have any question about the linear recurrent mode here? I apologize, I did not catch that.
Okay, we're not understanding you.
Text,
Could you
did you
maybe ask your
catch
question
that?
in chat? Okay, so another paper on attentions in RNN. Yeah, I don't think we'll
Thank you
have
for that.
a lot of time to explore this, so maybe something with regards to time. So I have like maybe 15-20 minutes until I have to leave, so
Okay.
yeah, just let you know.
Does anybody have any particular items they'd like me to dig into in the last few minutes? We haven't looked at this yet, which is the SSD algorithm.
To be honest, I think we've had like a lot to digest already. And I'm also a bit tired, and it's also super hot, so I don't know about other people, but I think it would be fine if we didn't dig too far, because yeah, I'm having troubles, yeah, a tiny bit of trouble staying awake, so I don't know. Maybe what else did you want you to cover?
I'm happy to wrap it up if people are running out of steam. This is an extremely dense paper that is building on a lot of material which they have been developing over quite a few years. It does feel, though, that they have come across something which is a really elegant implementation. And although I have yet to see any large implementations or training done on Mamba models, I think there's an opportunity here to actually go build stuff with it. The math is elegant.
True, but I think if there was some people saying, well, not saying, but I think it might have been discussed a bit in the off topic about people from like industry labs or industry being a bit skeptical of Mamba, that okay, apparently they would have tried it and weren't so convinced about it. So yeah, there's still the okay, they have an algorithm. Uh, the big question is, does it scale? And I don't think there's been a super clear answer for that with Mamba yet, unless but I'm not exactly super like following the literature a lot on this, but I don't know. So yeah, it remains to be tested at scale. That's the big thing.
Of course, it doesn't help that their prior implementation of Mamba, which did include CUDA kernels, was really quite different than anything being done in an industrial lab right now, which means it would have required quite a bit of convincing of management to even attempt to explore this at scale. And right now they have something that works really well, and so why stop? But I do think that the performance improvements possible by doing something like this are not small, and it's important that we explore more potentially computationally efficient methods, if for no other reason than it's hot today. That is, it's important for the world that we at least try to develop more efficient algorithms for all of this. We now know that machine learning is a real thing, and we owe it to the engineers to do it as quickly and efficiently as possible.
Yeah, true.
And with that, thank you so much for inviting me. I enjoyed this today.
Yeah,
Yeah,
you're
this has
welcome.
been fun.
So yeah, I think
Thank you so much.
this is a good time to maybe wrap up. Some quick thoughts. So I think the discussion on RWKV was interesting, and I think it might be worth like going deeper on it. Like I've been confused by trying to read RWKV, and when I'm confused, I'm a bit frustrated. So maybe we should add that to the pile of things to cover at some point. Yeah, I don't know if you want to do a second round on Mamba 2, maybe on more on the implementation, but that's something we can discuss. So anyway, so remember, there's also the another reading group on topological data analysis next week. I'll be doing that, so yeah, stay frosty. So I think I have nothing left to say. So thanks you again, Evelyn, for covering this, and thanks to everyone who helped with the discussion. That was very, how to put it, productive.
Thank you so much. Enjoyed this. Hope you'll have me back again sometime.
Sure. Okay, so I'm going to cut the
I
recording.
hope you all